we want to talk about today are just an introduction to filter banks and a gentle introduction to what wavelets are. Okay, so you may have heard about what wavelets are, and I want to talk about it a little bit. And so a lot of the theme of what we've been doing throughout the class, especially in the very first part, was representing a signal in a different way. And so, kind of a critical question is, what is a basis? Okay, so a basis is just a means of representing a signal, either a continuous time signal or a discrete time signal. So, for example, suppose that I have a 2D vector. Okay, so there are a bunch of different ways that I could represent that 2D vector, right? One is kind of the standard basis, which I would call like the, Cartesian basis, right? So, for example, if I had, let's suppose that we use a concrete example. So suppose I had 2 minus 3, right? I could write this vector as 2 times this vector plus minus 3 times this vector, right? That's the most easy way to represent the signal. In some sense, by putting the signal in these brackets, I've already represented it implicitly by that basis, right? But I could choose any two other vectors that are linearly independent to represent the same signal, right? So suppose I chose, these two vectors instead, right? I can solve a linear system to figure out that this 2 minus 3 can be represented like this, right? So it turns out that I can take any two-dimensional vector and represent it by something times the one basis vector plus something times the other basis vector. Or I could choose a different basis like this, and then I could find that I could represent that vector in this way. And so, kind of one way to think about this is that a basis is represented by a set of vectors in that space, right? So, for example, in this case, my basis vectors are unit vectors that are pointed to the right and up. In this case, my basis looks a little bit different. I've got one vector like this and one vector like that. And in this case, I've got a vector like this and a vector like this, right? And so you can see that in the first case and the third case, all I'm doing really is I'm rotating the coordinate system, right? And so all of these three things are what you'd call a change of coordinates, right? And whenever you did calculus type stuff, like when we went from polar coordinates to spherical coordinates to Cartesian coordinates, all that stuff was basically like a change of basis, right? So in many cases, we kind of prefer this kind of change of basis, where all I'm doing is I'm rotating the coordinate system, right, to make the coordinates kind of more favorable to me. And so if any of you have done like principal component analysis in a machine learning class, for example, that's one thing that you're doing is you're taking the original basis and then you're changing it to a more favorable one in which the first axis corresponds to the dimension where the signal is varying the most, right? So if you've taken Malik's machine learning class, you probably did some sort of PCA, right? So the point is that different bases have kind of advantages and disadvantages for representing a signal. And it turns out that all the stuff we talked about in the very beginning of class, Fourier series, Fourier transforms, and so on, are just different ways of representing a signal, right? So, for example, even though here I'm talking about vectors, the same idea applies to functions, okay? So, for example, for functions, one basis that we learned about, so suppose that we had a signal, suppose that we had periodic signals on the range minus pi to pi, okay? So in that case, what we found out from what was the very first lecture was that if I took that function, I could write it like a Fourier series. And these Fourier series coefficients were gotten by the inverse formula. right? And so the idea is that what I'm doing here is I'm representing my original signal as the sum of an infinite combination of basis functions, right? So the coefficient is playing the role of the coefficients here, and the functions are playing the role of these basis vectors, right? And so we know that fundamentally what I'm doing is I'm taking the signal, which could be anything, as long as it's periodic, and I am representing that like alpha 0 times the DC coefficient plus A1 times, cosines and sines that vary slowly, A2 plus cosines and sines that vary quickly, and so on. Right? And so, as we learned throughout the course, representing a signal like this, which is really looking at the frequency domain of the signal, has a lot of implications and a lot of good things for the kinds of signal processing tasks that we want to do in the real world, right? So we talked a lot about Fourier type analysis. In fact, that's almost all we talked about throughout the whole course, right? So what I want to just mention today is that there are other ways of talking about signals that are as useful as the Fourier transform, and in fact even more useful in the sense that the Fourier transform is not good at some things, right? So for example, if I were to look at a signal like this, right? So suppose I have a signal where, and I'm going to see if I can draw this. So this is kind of like an AM signal in some sense, right? So this is like a carrier wave that is modulated by some sort of envelope, right? Even though there's really only fundamentally one frequency inside that signal, a Fourier analysis is going to take, definitely more than one coefficient to be able to represent that signal properly, right? Similarly, if I have a signal like this where nothing much is happening, and then I have like some sort of a sharp spike and nothing much is happening again, Fourier series and Fourier transforms are awful at representing signals that are really spiky and really discontinuous, right? Because to make up this signal with a Fourier series, I have to make the signal up out of a lot of sine waves that have equal amplitude across the whole band, right? So it's going to take me a ton of Fourier coefficients to represent this signal. And these kinds of signals happen a lot in real-world electrical engineering applications, right? So when I turn a system on, I get this kind of maybe transient, boof from when the system goes on, then it settles out, right? So Fourier series are going to be bad at this. And even things that are as simple as, a straight line, right, that just keeps on climbing. A Fourier transform or Fourier series is not going to do very well at representing this, right? Because again, I have to make this, smooth linear ramp that is not oscillating at all out of a bunch of oscillatory, signals. And so in all these three cases, I would say, the Fourier transform, the Fourier series / transform is poor at representing these kinds of signals. And so you may have heard about wavelets, right? So certainly wavelets play a big role today in kind of modern image and video compression. So I just want to kind of mention what does that mean. And so, normally if I had more lectures, I could spend 4 or 5 lectures really developing the theory, which is actually pretty interesting. But let me give you kind of the big picture, okay? And so this is like the very crudest way of thinking about it, is that, what you learned about in class so far are kind of two bases for representing a signal, right? So I kind of have, if this is time and this is frequency, the first thing you learned about in signals and systems, for example, is kind of like a time domain basis, where if I tell you, okay, I'm going to give you n numbers to represent the signal, the first way you represent it is by actually looking at the signal at n given values in time. So that means that, in some sense, you get great time resolution because you know exactly what the signal is doing at every point in time, but that representation of the signal doesn't give you any sort of frequency information, right? Because all the frequency content is kind of tied up in every time domain signal. Every time domain signal we know corresponds to the sum of a whole bunch of cosines and sines. So then we kind of talked about the frequency basis, right? So kind of a frequency domain basis is more like this, where now I can ask you for telling me the frequency content at a fine set of frequencies, but each of those, each of those coefficients corresponding to one of these rows tells me about a sine wave that is spread out across the whole time domain spectrum. So there's no temporal resolution in a Fourier transform, right? I only get frequency that corresponds to the content across the whole signal, right? And so this is, the way I think about this is that if I gave you n numbers here and n numbers here, well, I could give you n numbers in a different way that would give me some both time domain and frequency domain resolution, okay? And so a wavelet basis, and this is a really sketchy picture, but it turns out to be kind of accurate, looks more like this. So if I was given the problem of, okay, I'm going to give you n numbers, and you have to divide this box into n pieces, each of which has equal area, right? So I could do it like this, I could do it like this, or I could do it like this. So, for example, I could have this be one box, and then I could have this pair of boxes, and then I could have this set of 4 boxes, and then I could have like this set of 8 boxes, right? So the idea here would be that I would get some sense of the lowest box tells me kind of like, it's like DC in some sense. It says, this tells me at the lowest frequency what's happening across the whole time domain. But then, like, this box basically says, okay, within this small, time window, tell me the frequency content, right? And so I can get this kind of like resolution that says, I can separate this time window from that time window and get different frequency contents, right? So this is kind of like the fundamental concept behind wavelet theory, is dividing up this box in a way that gives me a little bit of time resolution and a little bit of frequency resolution at the same time. And that's good for signals like this, where here, for example, there's a sharp change only localized in time, right? That has suddenly a lot of high frequency content that isn't present in the whole rest of the signal, right? A wavelet analysis would help me isolate automatically, hey, there's this point in time where there's this different frequency content, right? So that's one reason why wavelets are really useful, because not only does this kind of thing happen in signals a lot, but also in image processing, as we'll talk about next semester. In an image, if I've got, for example, a black region and a white region separated by this kind of edge, if you think about this in 2D, this is exactly the same kind of behavior. I've got like a step function behavior, and it's localized in just one region of the image. Wavelets are great for automatically picking out where those edges are and efficiently helping me to code them up, right? So one big issue in image processing is compression, right? And so if I know where the edges are and I localize them in space, then I can compress them more efficiently. So we'll talk a lot more about that if you take my course next semester. Okay, so this is the basic concept, okay? So now we're going to put this kind of pot on the back burner for a few minutes and talk about a concept that turns out to be related, which is filter banks. Okay, so we kind of didn't really talk about that at all in this class so far, but those happen a lot. Actually, we started to touch on it in the very last part of the last lecture on vocoders, right, where we're talking about how do I make this robotic voice. What I would do is I would pass it through a set of bandpass filters, all of which have stuff at different frequencies, right? And so the way that I would analyze and talk about such a system is with a filter bank. And so here's an example of a simple 2-channel filter bank. And actually, I'm going to talk about a very particular kind of thing, which is called a perfect reconstruction filter bank. So the idea is that I have a signal that comes in here. I pass it through a filter here, and I pass it through a filter here. So again, here I've switched over to discrete time, right? And so let's suppose that I have n samples in my original signal, okay? And now I pass it through an FIR filter here and an FIR filter here. So each of these, each of these FIR. So if I pass this through these 2 filters, then each one of these guys is going to give me n numbers at the output, right? And so the idea here is that I want to represent the signal with only n numbers totally, and if I do it if I pass it through two filters, I've got two n numbers, right? So what I'm going to do is I'm going to cut down each of the outputs of these so that at the result of the filter bank, I've got n over 2 numbers coming out of the top and n over 2 numbers coming out of the bottom, right? And so that's a way to represent the signal with, I had n numbers before, now I have n different numbers coming out, right? So again, you can think about what's happening inside this filter bank as changing the basis of the function, okay? And if I want to reconstruct the original function, if I want to switch my basis back to the original time domain, then what I would do is I would fill in some zeros here. I would filter these with some special filters we're going to talk about. And I would add up the results, and I would get some sort of reconstruction. And so the idea is that for this kind of system to work, what I want to do, and actually these guys are also FIR filters, what I want to do is I want to choose these filters in such a way that the output is exactly the same as the input, right? That means that I have not really distorted the signal at all. I mean, in practice, if these are causal FIR filters, I can't actually get exactly the same input because if everything is causal, the most I can get is a delayed version of the original signal, right? So the idea is to determine these filters so that this thing is just a delayed version of the original input. And this is called a perfect reconstruction filter bank. Okay. And kind of just like for, in some sense you can kind of see that you could think about this part as kind of like a Fourier transform, right? So I take the original signal, I do some processing to it, and I get some new way of representing the signal. That's like analyzing the original signal into this Fourier series coefficients. And then on this side, I'm reconstructing the original signal from kind of doing the inverse transform, right? So before I do this, let me just think about this for a second. So why do I need to have these two channels, right? Is it possible to kind of just have one channel where I change the filter, I change the signal automatically and just get n numbers straight out of here? So let me just pause and digress for a second. Could we do reconstruction, or could we get perfect reconstruction with a one-channel filter bank? So, for example, would it be possible to have, say, just one filter here, don't do any downsampling, have another filter here, and then get back the original signal? So, kind of, this is like an inverse filtering problem in some sense, right? And this actually comes up a lot in signal processing. We didn't talk much about it in this class. This would be kind of like one of the things that you could go from this class and extend it, would be to say, this is like some sort of a crappy, garbling, communications channel, and then G is the filter that I try and design to clean up that channel, right? And so, in general, suppose this is some FIR filter, right? So suppose this is like just, I'm going to choose an example. Okay, so here's an example FIR filter. It's kind of like a low-pass filter, and so that's like saying that my H of omega would be like this. So here, if I wanted to invert that filter, I would need to have a frequency response that is something like this, right? And again, if I think about this, this is an IIR filter, right? So this is FIR, and this is IIR, right? So if I was to actually work out the impulse response of this would look something like, it would be an infinite series. So the problem is that in general, the inverse of an FIR filter is an IIR filter, right? So if I want all these filters to be FIR, then I can't do it with one channel, okay? And even worse would be something like this. So suppose that I had something like this. Suppose my H was, 1/2, 1/2, right? And let's suppose that the X that I put in is something like an alternating high-frequency signal. When I filter this with that, my output here, I call that Y of n, my output here is going to be 0, right? Because, what do I think about this is that if I think about this as a pole 0 plot, here there's a 0 at pi, right? And this signal is exactly the frequency that's oscillating at pi, and so basically this frequency is getting entirely filtered out by this FIR filter, right? And so then there would be no hope of reconstructing my original signal from just zeros, right? So the problem is that if I only have one filter, it's possible that I've lost information by filtering it, and I could never get it back, right? And so kind of the cool magic of having a two-channel filter bank is that it's possible to always get exactly the original signal, even if stuff gets filtered out by that signal in here. So there's no restriction on what X can be to still have perfect reconstruction. So that's kind of a cool theoretical result. So let's talk a little bit about, how does the overall transfer function of the system work, okay? I know you guys are tired of Z transforms and stuff. We're going to do one more little bit lecture. Yeah?
So, the example here provided the signal was, it's the simpler frequency is probably not accurate. It's exactly an accuracy frequency. So it's not going to be reconstructed probably anyway, right?
Well, I want to be able to reconstruct any signal that I put in, right? And in some sense, I don't think that Nyquist should really come into the question, right? So, maybe the way I think about this is that I have a set of n numbers coming in, right? And I want to be sure that no matter what that set of n numbers is, I get the same set of n numbers coming out, right? So, that's an interesting point about how, in theory, I should never have sampled a signal to get this kind of behavior because it's on the edge. That's an interesting point, right? But I think it's better to think about this kind of topic in terms of straight-out linear algebra, right? So if I've got a set of n numbers coming in, I want to make sure that no matter what that set is, I can get the same set coming out the other side. That's an interesting point. So other questions or comments about this? Okay, so let's think about what actually is happening inside this filter bank, okay? So we have all the tools now that we need to analyze this. And so first let me look at a simpler system. Suppose I have a signal, it gets downsampled, it gets upsampled, and I get some output, right? So kind of like that's like saying that I have, an original signal, I chop out every other thing, and then I put in zeros for the things that I chopped out, right? So you can show that the Z transforms have this property. Not hard to show. This would be kind of like a good exam problem. I'm not going to prove it right now, though, because it's an easy proof. And so what we really have, though, is something more like this, where I have a signal that gets filtered by something, then it gets downsampled, then it gets upsampled, and then it gets filtered again. So kind of the top channel of that filter bank, I can kind of use this result to say that my output, Z transform, is going to be 1/2 times the filtered version of this thing. And so the overall result of putting the signal through two such channels and adding them up is going to look like this. So I'm going to just write this result. If I had another channel, it would look like this. And if I added these two things up, what I'm going to do is I'm going to collect these in terms of a part that only depends on x of z and a part that depends on x of minus z, right? So that means that my sum of these two things, so overall output would be the sum of these two things, which is going to be a part that depends on x of z only, and a part that depends on x of minus z. And so the way I think about this is that, this first term represents some sort of a distortion of the original signal, right? Because remember, what I want is, we want that y of z is just some sort of a delayed version of the original signal, right? That's what we want. And so that means that the top part is telling me how the original signal is being distorted, and the bottom part, you can kind of think about that as some sort of like aliasing, right? Because x of minus z is like flipping the frequency domain around the middle. So this is kind of like distortion, and this is kind of like aliasing. And so for this to happen, what we need are two properties, right? For no aliasing, we need this whole second term to be 0. And for no distortion, just delay, I need this term up here to be equal to 2z to the minus l, right? Just a delay. So these are the conditions that I would need to have perfect reconstruction, right? And so the idea here is that, remember, what I have is a bunch of freedom to choose G0, H0, G1, H1, right? So I've got 4 FIR filters that I can screw around with to be able to try and make these conditions happen, right? And so it turns out that there are some easy ways to meet these conditions, okay? So let's think about getting rid of the aliasing first. So for getting rid of the aliasing, so let me just kind of keep this up here. So to remove aliasing, I can make a choice about how the G's and H's are related, right? So what I could do is I could say I am going to choose G0 of z to be equal to H1 of minus z. And I'm going to choose G1 of z to be equal to minus H0 of minus z. That means that this is going to turn into G0, G1 minus G0, G1, right? So this is basically saying that no matter what I chose as the H's, if I choose the G's in a certain way, then I can remove all the aliasing, right? So that kind of means that I have removed half of the filters I have to design by using this. And so kind of what that means is that if I have, a set of H's, so say these are kind of arbitrary FIR filters, and say they're centered here, then that means that my G0 is going to be basically a modified version of this, where I'm flipping the signs on some of these guys. And my G1 is going to be something like this. And so you can show that if this is low pass and this is high pass, which is something that we're going to want in a second, then that means that this is also low pass and this is also high pass. You can show this by kind of writing out the Z transforms. And that's in some sense, I guess I should have said this a little earlier, but that's in some sense what we're trying to do here is that we're saying, okay, what's the point of passing the signal through two different filters in the first place? What I kind of want to do is I want to separate their frequency in different bands, right? I mean, it wouldn't make a lot of sense if both of these filters covered the same frequency band. Kind of what I generally want to do is I want to have a low-pass version of the signal here and a high-pass version of the signal here. And so that kind of gives me some sense of what's happening at low frequency, what's happening at high frequency. Okay. And so that means that I can get rid of aliasing entirely just by fixing two of the filters as functions of the other two filters, right? So that's super easy. And so that means that if I look back at my equation here, that's like saying, well, you know, G0, H0, and G1, H1, now I can replace what I know about these Gs, right? So I can say, okay, if I define P0 of Z, which is the product of these things, then this other thing up here, G1 of Z, H1 of Z, becomes, I can plug in what I just said. This would be minus H0 of minus Z. This would be H1 of minus Z. Oh, wait a second. What I mean to say is this would be minus H0 of minus Z. This would be G0 of minus Z. And so this whole thing would be minus P0 of minus Z. And so what I can do is I can write my no distortion condition by saying this is like P0 of Z, and this is like P0 of minus Z. So now I've kind of like subsumed the G and the H into one single filter that I have to think about. And so, let me write that again here. So the no distortion condition can be written as P0 of Z minus like this. So basically, remember that, you know, P0 of Z is equal to these two things. And kind of by definition, you know, this is a low-pass filter, this is a low-pass filter, so this is also a low-pass filter. And so kind of the name of the game is, number one, I want to design a low-pass filter, P0 of Z, satisfying this equation here. And two, I want to factor or split the filter that I designed into two other low-pass filters, and then get G1, H1. Right? So everything kind of comes down to designing some low-pass filter that has this property. And this is called a half-band filter. And again, this is actually not that hard of a process, right? Because certainly the second part is not so bad. That's like saying that if I have some FIR low-pass filter, to basically factor into two different low-pass filters, all I need to do is basically assign some zeros to G0 and some zeros to G1, or to H0. So it's kind of like I'm taking the zeros of the original filter and I'm splitting them off into two smaller low-pass filters. And again, let's think about what this condition implies. Okay, so let me just do a quick example. So let's suppose that I have some generic thing. Suppose I have, you know, P of Z is equal to A plus BZ inverse plus CZ inverse like this. Okay, And then what is P of minus Z? Well, it's going to be A minus BZ inverse plus this. So basically that's going to flip the odd valued things because of the evenness. And so if I subtract these two things, then I'm going to get like this. And I'm going to get 0 plus 2B Z inverse plus 2D Z minus 3 plus so on, right? So kind of what this tells me is that this condition puts no constraints at all on, A, C, E, and so on, right? So that means that I have freedom to design half of these filter taps myself. And then this condition says, okay, if I want this thing to be equal to Z to the minus L, that means that one of these guys has to be 1/2. So that means that, one odd coefficient has to equal 1/2. The other odd coefficients have to equal 0, and then there are no constraints on the even coefficients. Right? So that kind of gives me a lot of freedom to design these half-band filters. And so let me give you an example and then kind of show you how this thing would work. So for example, what I might do is I might say, okay, let's take P0 of Z equals, and I'm going to just kind of factor it out for you like this. If I were to write this out, what I would have would be this. So here's a choice of a filter that satisfies my constraints, right? It only has one non-zero odd power of Z, right, the middle one. And then it's got zeros for all the other odd powers of Z, and I've chosen these other things kind of arbitrarily, and I made sure that the odd power of Z in the middle has a weight of 1, basically, right? And so here, basically this is like L equals 3, and I can show that this minus this equals 2Z like this, right? So I'd have a delay of 3 units in my system if I used this filter, right? And so, again, I can think about where are my, poles and zeros, right? So this guy has, 4 zeros at Z equals minus 1, and it has zeros at 2 plus or minus square root of 3. So it's got a couple of complex zeros and a whole bunch of real zeros. And so then I have a bunch of choices about how I can apportion these zeros into these two different G0 and H0 that I need, right? And so, for example, let me just make a little table. So if this is my original polynomial, then let's think about how I could apportion those zeros. That's like saying, okay, so if I have G0 and H0, well, one possibility is, I could just have one of these filters be 1. That's like just passing the signal straight through. And the other signal would have all the zeros. Or I could say, okay, I'm going to take one of these guys over here, and then I'm going to leave all the rest of the zeros over here. Or I could take, for example, 2 of these guys and leave 2 of these guys over here. Or I could take 1 0 here, and I could take basically, one of these zeros over here. I don't want to list like all the options, but basically I can kind of keep on going like this, right? Or I could, let me just show you one more option. I could say, okay, I'm going to take these guys here. And so kind of the reason that I'm enumerating these options is that each of these choices has a different kind of implication for how the filter bank behaves. I guess I can say one more choice here would be like this. It's like saying take half the zeros here and take half the zeros here. And so, you know, why would I want to do one or the other of these kinds of options? Well, for example, you know, this guy is kind of nice, this guy here, because both these filters are symmetric. That means that they have linear phase, and we already talked about in FIR filter design that linear phase was good, right? So both these guys have this kind of nice, you know, symmetric around the middle tap property. So, you know, that might be something that would be nice. This guy might be nice in the sense that this filter over here is really easy to apply. It's like a very simple, you know, low-pass filter, just filtering, you know, like with 1-1, right? So on one end, this would be pretty easy to apply. This would also be linear phase, as it turns out. And this guy also has some nice properties. It's not linear phase, but it's what's called orthogonal, right? And what orthogonal means is that, you know, so this guy has nice properties in the sense that if I write out what the filter taps look like, they look something like this, where, you know, I get an orthogonal filter bank where I'm kind of forcing the filter taps to have a specific pattern. So it's like saying that I already knew that I already knew that H0 and G1 were related by something like this. But it turns out that also, if I make that choice, I get the same numbers appearing in these guys. So it's kind of like saying that if I wanted to, I could try and make all the filters fundamentally depend on the same numbers, and I would just be choosing the numbers in the first low-pass filter, right? That's kind of like the difference. I mean, it's a little bit subtle, and for the last day of class, I don't want to get into a lot of deep stuff, but it's kind of like the difference between a basis like this and a basis like that, right? So we kind of like to have bases where it's just like a change of coordinates. It turns out that, you know, this choice here kind of corresponds to a choice like this, where I'm just changing the coordinates nicely, I'm rotating it around the center of the space, whereas something more like the one I showed you earlier, you know, something more like this has the result of, it could be that the two filters are doing something that's kind of like this, which is a little bit less exciting, but it gets the job done. And you can read more about this. I mean, there's a lot of stuff about this in the book. An early, kind of an early related approach was what were called quadrature mirror filters. And you can kind of read about those in the book. The idea was basically that you want to have the frequency responses, like if this was the frequency response of H0, that you wanted to have the frequency response of H1 be like exactly mirrored around, you know, pi over 2, basically, right? So that would be basically like saying H0 is a low-pass filter, H1 is a high-pass filter, and I exactly get the same filter if I flip it around the middle, right? But it turns out that you can actually design very good quadrature mirror filters that are not like kind of useless. Okay, so let me kind of bring this back to what I started talking about in the very beginning, which is how this is related to wavelet transforms, right? So in practice, what I do is, so the big picture is, I design my half-band filter, I make some choices about, you know, how I factor that into these polynomials, those FIR filters, and then what I would do is I would say, okay, I'm going to take my original signal, and I'm going to pass it through the first layer of the filter bank. And here I'm going to kind of flip it around so that this is like the high pass part, and this is like the low pass part. And then I'm going to downsample this by 2. Okay, so it's kind of like saying, okay, you know, I have n numbers here, and now I still have n over 2 numbers here and n over 2 numbers here. Then what I'm going to do is I'm going to pass these guys through the same filter bank again. And again. Oops, this is not a thing. And so on. I basically keep on doing this as many times as I want. And so the idea is that, you know, if I had n numbers here, then I'm going to have n over 2 numbers that come out of my very first high-pass filter bank. I'm going to have n over 4 numbers that are kind of like, you know, low-pass filter, then high-pass filter. Then I'm going to have n over 8 numbers here, n over 16 numbers here, n over 16 numbers here, right? And so kind of the way I think about this is that the thing that I get at the very lowest end, so kind of like the thing that I get over here is basically a kind of very, you know, short or small, you know, very low-pass filtered signal. And then the stuff I get up here is kind of like, this is like kind of high level or high frequency detail. And then the stuff over here that I get out of these guys is kind of like mid-level details. Right? It's kind of like saying, I think this is most convenient for me to think about in terms of images. It's kind of like saying that if I start with an image here, what I come out with at the bottom is like a very small, very blurry version of the same image, which is still useful in some sense. I get a sense of what that image looks like. The stuff I get out at the top is going to be like the highest frequency edges or jumps in the signal. And then here it's like I'm taking a smaller, blurrier version of the signal and finding the edges there. Here I'm taking a smaller and smaller, blurrier version and finding the edges there. And so the idea is that what I kind of get is frequency content, frequency jumps at different spatial levels of the signal. And that kind of ties back to the picture that I was drawing earlier, where the kind of effective decomposition I get is something like this, right? Where this here is kind of like saying, this is like my blurriest version of the signal, this is like my highest detail version of the signal, and these are kind of like mid-level details, right? So here I get a lot of frequency resolution at different points in time, and here I get, you know, like a very broad low-pass version. And so in practice, you know, and then if I put all this stuff back together on the other side of the paper and I apply my reconstruction filters, in theory, if there was no corruption in any of the outputs of any of these filter banks, I would get exactly the same signal that I put in, right? But the real use of this kind of tree of filter banks is for compression, right? So the idea would be that what I would do is I would put all these guys through some sort of a compression algorithm, which is kind of related to like the quantization stuff we talked about last week, where basically what I would do is I would quantize these coefficients at various levels, and that would hopefully make my signal a lot more compact, so that when I reconstructed it on the other side for these quantized coefficients, I would get something that looked pretty much like the original signal, but it would use a lot fewer bits, right? And so, for example, things like the JPEG 2000 image compression standard are using wavelets under the hood to compress the images, right? And so, kind of like, I'm not going to draw the whole other side of the diagram, but basically the idea was that I would have kind of like, you know, my tree of stuff, and then over here, this would be like my kind of, you know, channel where I would compress and quantize things. And then to reconstruct, I would basically, you know, build back up. to get my reconstructed output. And so this is what's called a multi-resolution or a multi-scale analysis, right? This is very different than the kinds of things we talked about so far, where fundamentally I'm kind of keeping all my frequency analysis at the same scale. Here I'm kind of doing different amounts of frequency analysis for different sized signals. So it's a very interesting kind of analysis. I mean, one thing that I'm still not tying back to, and the reason I'm not is because it would take another couple hours to get there, is what do the basis functions for this kind of system look like, right? So certainly the basis functions I'm decomposing the signal in terms of are not sines and cosines anymore. They're actually kind of very weird shapes. And so, for example, and this is going to be a crappy drawing, but it's kind of like saying that what I'm doing is basis functions for wavelets look really strange. One way of thinking about it is that, the very simplest basis functions for wavelets look like this. So maybe they can look strange. So for example, there's a set of wavelets called Haar wavelets that basically look kind of like this. And so the idea is that, this is my lowest frequency analysis. This is like the average value of the signal. This is something that's kind of like, again, these are all like time domain signals. It's not like frequency domain, it's like time domain. This is kind of like saying I take the first half of the signal and I subtract the second half, right? But then you can kind of see that these other basis functions are very local, right? This, for example, at the lowest level is like saying, take signal value 1 and subtract signal value 2. That kind of tells me kind of a crude high-pass analysis of what's happening in the very beginning of the signal. And this is kind of telling what's happening in the middle, and this is kind of what's happening at the end, right? And so the nice thing to see is that fundamentally all of these basis functions are like squished and shifted versions of the same function. There's this kind of like recursive self-similarity property that makes the analysis really interesting. And so it turns out that really, to define wavelets, all you have to do is define kind of what they call this mother wavelet, and then everything else that you have is basically squished and shifted around. That's a really interesting thing from a mathematical point of view. And here you can also kind of see why wavelets are called that, right? Because these things look like little waves, but they're very local, and they are only, they're either big waves or small waves that are localized in different places. And it turns out that, you can get very weird-looking basis functions instead. So your mother wavelet might look like some sort of like bizarro, jaggedy function that you would never think would be a good decomposition for a signal, but you can show that for real-world signals, like speech and image signals, sometimes these bizarro wavelet functions actually do a great job of compression, right? And so there are these things called Dobschi wavelets, which are, kind of weird-looking, but do a great job, and that's what everyone uses for compression. They don't use these nice square things, they use these strange functions. And finally, the great thing about wavelets, the reason that this is not just some sort of mathematical toy, is that this multi-resolution, wavelet transform, right? So basically, there turns out to be a DWT, discrete wavelet transform, which is kind of just the same as the DFT, the discrete Fourier transform. It turns out to be order of n operations. Whereas all of the FFT algorithms we talked about were order of n log n, right? And so wavelets can be accomplished extremely efficiently, right? And the efficiency gains kind of come from how easy it is to kind of recursively filter the signal at different scales, right? Because here, I spend maybe some computation doing things at the highest scale, but as I go down lower scales, I'm filtering shorter and shorter signals, and so that's kind of where the order of n comes from. And so, in some sense, the whole thing is like a total win-win, right? I've got a thing that, number one, turns out to be great for representing local variations of signals, Number two, is extremely efficient to implement, and that's why lots of real-world signal compression algorithms are using wavelets these days instead of Fourier transforms, right? So again, this is the kind of thing where, if we had more time, I could lecture for 2 more weeks on really developing the wavelet theory and talking about it, but this is like kind of, what you might see in a more advanced DSP course going forward, right? And you can even have a whole course, I took a whole course in grad school on wavelets, period, and spent the whole semester on it, right? So it's interesting stuff. Okay, so let me pause and ask, even though I know that it's pretty high level. So questions or comments about that? Yeah?
So from what you're saying, it seems like the discrete wavelet transform is a lot more popular and so, more efficient in a lot of ways. Why isn't that we spend so much more time on the FFT and there's so much more?
Right, so why do we care about the FFT if wavelets are so great? So one of the reasons is that, so I should kind of have prefaced my remarks by saying that the wavelet transform is great for compression. Okay, and so since I'm kind of an image processing guy and I think about compression sometimes, that's one of the reasons that I know a lot about it is because it's extremely popular for squeezing information out of a signal. But all that being said, there is this whole kind of, almost all of electrical engineering is based on the theory of what's happening at different frequencies, right? All of our communication theory is based on frequency analysis and stuff like that. And I think it's fair to say that wavelets have not really penetrated communications theory very deeply in terms of things that your communication systems are doing. Are not going to use wavelets for doing that kind of analysis. And so for things like communications theory, control theory, and so on, where so much of the way of thinking about a system is in the frequency domain, right? Because we want to know what are the modes of analysis of a signal, right? Those are places where we still want to talk about the Fourier domain, right? So wavelets are best, I think, from a computational point of view, right? That's maybe the bottom line, is that if I have to squeeze all the information out of a signal as efficiently as possible, then I should be using wavelets instead of the Fourier transform, right? But if I want to understand and design a system, right? So when we design filters and stuff like that, all that stuff is inherently a frequency domain concept, right? We want to know, how does a filter shape the frequencies of the incoming signal, right? And that's something that we really can't talk about with wavelets, right? That's a frequency domain kind of concept. So it's kind of a situational thing about when you want to use different things. It's a good question. I guess I kind of oversold them a little bit because I was thinking about compression, but there is a lot of stuff that we can't do with wavelets from the world of communications theory and electrical engineering, right? Like all the stuff that you guys analyze with oscilloscopes and hardware, right? That's all still inherently frequency domain, Fourier transform stuff, right? Circuit theory, when you think about what resistors and capacitors do to signals, is all about how they modify sines and cosines, right? There's no circuit theory for wavelets, I don't think, that makes any sort of sense. So, other questions? Yeah.
We transform it and we get a spectrum right? Time and frequency.
Right.
So we have a 2D image of essentially of a 1D signal.
I wouldn't necessarily call it an image,
yeah.
Right? It is true that you can think about. It's tough for me to separate because I always think about wavelets in terms of images anyway. But
that's kind of where I'm getting to.
Yes.
How do you represent a 2D signal image in the wavelet transform? What does it actually
Right.
look like? What does the result look
Right.
like?
So let's talk about that for a second. So to go into the 1D case for a second, what I'm doing with a 1D wavelet transform is I'm fundamentally saying I'm representing my original signal some coefficient times this plus some coefficient times this. So basically, this is the decomposition of 1D. You can think about it as I'm separating my original signal into a sum of basis functions in exactly the same way that we drew these as sines and cosines for the Fourier transform, right? For an image transform, you're basically doing a wavelet decomposition both in the row direction and the column direction. And so actually, it's probably easiest just to show you, I'm sure we can find a picture of it. So So kind of here is an example. Let's see if I can make this bigger. Why do I suck? Should be able to just like, crap. Bing. Why can't we use Google like normal people? All right. All right, let's try this again with the Google image search. I found the same image, but I can now make it bigger. Okay, so kind of what you're seeing here is that this is not really the best example, but here is basically the effect of the, so here this is like a 2-level wavelet transform, right? These are the edges that are most important at the highest level. This is like if I high-pass filter the signal twice in both the vertical and horizontal direction. And then here, these are like the high-pass edges that are most important at the original resolution in the left-right direction. So like, for example, I have a strong edge in the castle here that's coming out as strong edges here. And then these are the edges that are most important in the vertical direction. So for example, like the top of the castle responds strongly here. And then these are like lower pass versions, and this is like, let me see if I can find a better example than this, because this is kind of like, Star Trek people. So this may be better because it's kind of like line art. Right? So kind of here's an example where this is just like a 1-level decomposition. So here, these are the finest edges that are important in both the horizontal and vertical directions, which are pretty small and hard to see. These are the edges that are most important in the kind of vertical direction, right? So these strong edges in the water correspond to strong edge responses here. These are going to be the edges going left to right, and so there aren't that many of them, but maybe where the face meets the hair, you see some response. And this is the low-pass version. So if we had like just one better example here. Whoa, what happened here? You could argue that I could have prepared for this lecture better. Let's try this. This is French. Again, this is kind of like, again, looking at multiple scales. So the lowest scale is like this super blurry, small, low-pass filtered version of the image. And then these guys tell me kind of like what edges are important at different scales in both the horizontal and vertical directions. And if I were to basically blow these images all up to the same size as the original and add them together, I would get the original image, right? And so the argument would be to compress. Maybe what I might do is I might take all these edges, which are using 1/4 of the coefficients, and maybe I could set all these edges equal to 0. And if I reconstructed the image, it would look pretty much like the original one, right? And I would gain, substantial compression. Or maybe instead of getting rid of them entirely, I quantize them so that instead of having 256 gray levels in the edgiest image, I only allow myself to have like 4 levels in the edgiest image, right? Then I'm saving myself 6 bits of 1/4 of the coefficients, and that gets me some compression gain, right? Something like that. Does that make sense?
Yes. So we need this kind of cascading.
Yes.
Into the image.
Yes, that's right. It's kind of like a cascading version of the image. That's right. Other comments or questions? Yeah.
So it's, as nowadays the memory size of anything is like increasing dramatically, doing like.
Yeah. Why do we
care that much?
So yeah, in the world of when everything is fast and cheap, do we still care about this kind of thing?
Yeah.
I think that we do. I mean, like, you always want more bandwidth, right? And so, for example, I think that things like wavelet video compression are probably what are going to enable you to stream HD video to your iPad, right, over a wireless network link, right? So these kinds of things apply to video just in the same way that they do to 1D signals and 2D signals, right? And so you can imagine that, a DVD movie, right, is still gigabytes of information, and that's already compressed, right? If you uncompress the DVD movie, it would be hundreds of gigabytes, right? And so if you want to stream that, to a device, then, and if all of you want to stream the same movie at once in this room, right, you're going to severely put some constraints on the network. And so I think that even though bandwidth is cheap or bandwidth is getting bigger and processing power is getting better, you still want to squeeze all the gains that you can out of the system, right? Just kind of a tangential thing, but since you're in the Smart Lighting Center, one thing that's kind of cool that we're talking about in the Smart Lighting Engineering Research Center is something called visible light communications. So the idea being that right now all of you guys are using and competing for the same resources, all the same Wi-Fi resources, right? But it turns out that what you could do is communicate information to your device by modulating the frequency of the light in the room, right? So, for example, if you want to get a steady light in the room, your eye is not sensitive to changes that occur much above, some kind of critical frequency, like 60 hertz, So if we're modulating the lights at hundreds of hertz or thousands of hertz, we can use that to communicate digital information. And you can imagine that each light in this room might be communicating slightly different information to different people in the room. And it turns out that the capacity of that light channel is extremely high, much higher than Wi-Fi. And so that's something that we're kind of trying to put together. Is you can imagine that, and they're already kind of starting to break this out in the real world. Like I think that there's a spin-off company called BiteLight that is doing pilot tests in places like Walmart and Target, where they're using the massive lights that they have in those huge spaces to direct information to customers, walking around the aisles, right? So again, there's kind of an argument for, you've definitely all been in situations where the capacity to your home computer or to your wireless device is slower than you would like, right? Even though we've gotten a lot better, you still see buffering, right, sometimes. And so the faster we can push information through and the more efficient we can do it, the better, right? And kind of another argument for why we still might want to do wavelets is we still should be concerned about the amount of processing it takes at the receiver side to reconstruct the signal, right? So if I can reconstruct the signal with an order of n decoder as opposed to an order of n log n decoder, that will make my device much more efficient, and it will make buffering a lot, or not, it won't be buffering, but it will be quicker to reconstruct the signal. I'll need to buffer less because I don't need as much time to undo my processing, right? Is one way to think about it, right? So I think we should generally still be thinking about these kinds of things, even though, life is pretty good, right? I mean, kind of the argument is that when I was, back in the day, right, before they had really, like the first version of Microsoft Windows that I used was probably like Windows 3.1 or something like that. And the only option I had for images was bitmap, right, where basically every pixel was coded with the same 8 bits. There was no compression at all, right? And then, of course, now we all know about JPEGs and PNGs and stuff like that, right? And no one uses bitmap anymore, even though, sure, I could easily transmit a 2 megabyte bitmap file. I could do that, but I mean, why wouldn't I transmit the 40 kilobyte JPEG file? That's much faster and more efficient, right? I mean, I think those things are still important. Okay, so let me just wrap up with just a couple of comments about things that are kind of, directions of DSP I didn't really talk about. So, one thing that like I said, I didn't talk about in class because, frankly, I find it kind of boring, but it is important. And so if you were going to talk about one thing that I probably should have talked about but didn't, it would probably be power spectrum estimation, which is basically, the short form of it is that it's like the Fourier transform of the autocorrelation of the signal, right? So it's a way of getting kind of frequency analysis from the signal without doing a full-on FFT. It's kind of a different route to getting frequency analysis. It's kind of like a coarser or smoother frequency analysis than you get with the FFT. But some of you, I think, are using it in your projects to get kind of like the basic peaks of things in the frequency domain without taking a full-on FFT. So there are different ways of doing this, and that's kind of like at the back of the book. One thing I didn't talk about at all, again, because I find it kind of boring, is filter structures. Again, I think this comes in the category of boring but important. So basically, whenever I have a filter, FIR filter or IR filter, there turned out to be lots of choices about how do I decide how to implement that filter. We kind of touched on this a little bit when we talked about polyphase filtering, for example. Like we talked about how I could implement that filter directly, or I could split it up into smaller pieces and use a delay chain to filter in a way that wasn't, well, the thing is that, if you really get down to the nitty-gritty and you think about, okay, so if I've got some noise in my signal or some noise in my filter, different ways of implementing the filter are going to have different implications for how that noise gets amplified and screwed around with in the system. And so it turns out to be important in some real-world systems to decide how do I actually decide to implement that filter once I've designed it. And so, again, if you page through the book, you'll see parts I skipped over that kind of show filter structures that are kind of equivalent filter structures for the same underlying filter. So you could talk about that. I guess one other thing that I would say is that there are definitely advanced topics. So we kind of very briefly touched on things like wavelets. There's also some really cool, more recent work on what's called compressive sensing. And Dr. Wang in our department teaches a whole course on compressive sensing. Now that you've had the DSP course, of course, I think many of you are graduating, but I mean, if you have or have a chance to take that course, it's kind of interesting because it kind of is related to this idea that a signal may not be, kind of the way I think about it is that there may be a basis where representing that signal is very sparse, right? So right now we take n numbers in the time domain, we convert them to n numbers in the frequency domain, and most of the time, you just get n different numbers, right? But it would be great if you found a way to represent that signal so that you took the n numbers here, and when you did the transformation, you got maybe like 3 really big numbers and then a whole bunch of zeros, right? So there's like some special world where if you move that signal over, you find out that it's actually very sparse. And sparsity is a good thing, again, from a computational point of view, but also from kind of like a signal understanding point of view, like understanding that really the signal is not, fundamentally that complicated if you think about it in the right way. There's a whole world of analysis of what's called compressive sensing that's kind of cool. And those kinds of techniques allow some very sophisticated systems. So for example, instead of taking an image of a scene or taking a radar reading that has like 100,000 elements, instead what I can do is I can kind of randomly send out projections into the world and only get a few signal responses back, and that allows me to reconstruct the original signal without having all the information that we might need according to the Nyquist rate, for example. So you can get away, this is a way of kind of circumventing the Nyquist rate in some sense for certain kinds of signals, which is really kind of neat. I think that's what comes to mind. Is there others? I mean, of course, also, again, I know that to the disappointment of some people, there's a lot of hardware implications and stuff like that that I didn't talk about at all in terms of how to actually make this stuff work on a system. I mean, a lot of you guys are figuring this out for your projects, which is great, but I'm not the guy to teach you the hardware stuff. Other things that people thought they should have seen in this class but didn't, and you were disappointed. All right, so I guess I did an okay job. Okay, so like I said, now you guys should have the basic tools to undertake, for example, a communications theory course, control theory course, compressive sensing. There used to be an advanced DSP course in this department. I'm not sure we still have it. Image processing. So basically, next semester, my course on image processing is it's not going to be like a 2D extension of DSP. I mean, for one thing, I think image processing is a lot more fun because you're really able to understand why you're applying all this stuff to these images, and you can see the results of what you're doing, and you know why you want to do it because everyone has used Photoshop to touch up an image and make it better, right? So I think that image processing is a lot of fun because it's much more immediate. So I hope I see a bunch of you in that class. I think that'll be a fun class. So I think that hopefully now you have the basic framework. I think that when you come out of signals, you only know like the very kind of basic stuff. I don't think you can come out of signals and understand how to design a system that does things, right? Hopefully now you have a little bit more tools in your toolbox to understand how you design filters, how you design, what are the implications of designing a quantizer, what are the trade-offs in designing certain things. So I hope you got something out of the class. Let me stop my